Hi guys, so we used the geometric module from phase 1 because it's very accurate. So we got this area 1, area 2 and area 3. These are the formulas for the areas, and then we started with area 2 and area 3 because area 2 is like a rectangle, so that's easy. And then for area 3, we had this formula because it's a triangle, so x times y divided by 2. And we got the starting point that is going to be 0, and then by simplifying all that we get this, and by substituting by these ones we get 0.016. And then this is the formula that we had, and we simplify it, and then we substitute it with the formula that we already had, that's m. And here it's substituted. Woo! Okay guys, so first what we're gonna do is sum the A2 area with the A3 area, okay? So this will give us 2008.47y meters because we previously multiplied it, okay? Plus y squared divided by 2 multiplied by 0.016, like my friend described previously, okay? So we know that the A1 area is 49.9 meters, but obviously we will multiply it by y, okay? And we have two formulas, which is it's a piecewise function, okay? So if y is 0.12, and this is the formula, okay, which is a2 and a1 sum, okay? And but if y is more or equal than 0.12, it is the a1 area multiplied by y. And because we don't want to do the module at area, we need the volume. So this is the formula of the volume, okay? So the area evaluated in y multiplied by the width, 21. Hello, so as you can see, we already got the volume, which is 21A times area. Okay, so we are now going to find out how much time it takes to actually reach that volume to fill up the whole pool. So we are relating the volume to time, to volume over time, and the constant rate that we are using to fill up our pool is 60 liters per minute, which is when you make the conversion 0.06 cubic meters per minute. And then we go over here. So now we're going to find out how much time it takes to fill up just this area, which is A2 and A3. There. Yes, we isolate the t because that's what we want to find, and we get basically our volume over the constant rate that we are using right here, and this we multiply it by over here. This, which is it's basically the area, right? So our in this formula, our y is the height of the pool the height of this specific area of the pool, which we already know it's 0.12. So we just substitute this into our formula. It's right here. Yes, we substitute all our y's for the 0.12 to get because it's the height, and we get that it takes 1,237.74 minutes to fill up this area. Okay, now to find how long it takes to fill up the A1, so the main portion of the pool, we are using the same relationship with times the area, which is 49.99 times y, which is our height. But for that portion of the pool, the height is 1.62, so that's what we substitute in there, and we get 28,344.33 minutes. Ooh, what did I go? 33 minutes, and then to get the total amount of time it takes to fill up the whole pool, we just add those two numbers together, and we get 29,582.07 minutes, which is approximately 20 days that it takes to fill up at 60 liters per minute.
And we're next to the pool that we just measured. So the final time it will take to fill up would be 29,582.07 minutes. We're gonna start with the rate of change. So we had our first figure, which so we got our final volume equation, which is gonna be this. The area equation times 21 is gonna be equal to the volume. And the first one of the piecewise function when it is less than 0.12, the value of y. And then we're gonna do the other one, and it is the other part of piecewise function. It is 49.99 times y times 21 is gonna be the formula of volume. This is gonna be our piecewise function for the volume, and we're gonna graph that in decimals. And it's gonna be like that. And then we gotta derivate everything. So the derivative of the first one of the piecewise function would be this, and the second one would be this. And this is our piecewise function derivated. Right. And this is the other function that we're gonna graph in decimals. And this is gonna determine when the water height changes when the volume changes with the derivative of volume and height. Now I'm gonna show the decimals. So here are the functions represented graphically in decimals. So we got that so I represented the red graphic as the volume function and the blue line as the derivative function, and I think it is pretty clear what it means. Examples that an AI helped me do, and I think that they are very accurate with the ones I did with decimals. So that was a way to prove that I was right and help me. That was a great method to help me prove that I was right. And that's the end.
Hi teacher, so the level of water increases faster when the area is smaller and slower when the area is bigger. So in the first part, in area 1, when it is bigger, of course the water levels increase slower, in y terms. But in the area 2 and 3, it increases faster because the area is more little. So the y increases faster.
But there's actually a faster water level change, which is in the ramp.